All right, let's get started with this workshop. I'm doing this from, well, sort of not live. I'm re-recording this because we didn't get through all the questions that I wanted to get through in the workshop. So now I'm redoing this, gonna do this a little better, hopefully. So these are the questions I'm planning to get through. So we have 4 from using critical points or finding critical points. So minimums, maximums, those turning points, and inflection points using derivatives. So let's try to remember. Look at the camera here. Then 5 questions trying to explain various scenarios in terms of derivatives. And then another 5 looking at graphs and trying to identify inflection points, which I know we did and doesn't sound that hard, but you'll see the questions are a little trickier than we might think. Okay, so first ones here. This is asking us to find, let's go on to the next slide. These things, so intervals of increase and decrease, we know what these are. Local maxima and minima. So just maximums and minimums, so the turning points. Excuse me. Local here does not mean only local ones. A global maximum is also a local maximum in a local sense. It just happens to be a global maximum on top of that. So this is just basically saying, let's find the maximums and the minimums, but we don't need to figure out if they're just local or if they're also global. We'll just find the maximums and minimums. And intervals of concave up, concave down. In class, I was often calling this curving up, curving down. But these are kind of the more standard terms that are used in our textbook, and inflection points, which we know what those are. All right. So first 2 here, we'll start with the one on the left. As usual, you should, if you're watching along, you should pause the video, try to do this on your own, and then come back in a moment. I'm not gonna, I don't know, do like a fake countdown or whatever. Just I'll trust that you are pausing the video at appropriate times and trying these on your own. Okay, first one. So our process here, just so we remember, number 1, find the first derivative. All right, first derivative here is just f prime of x squared turns into 2x, and 6x turns into -6 here. All right, step number 2 is to find the zeros of the first derivative. Okay, so we set this first derivative equal to 0. And at that point, 0 is equal to 2x minus 6. So x is equal to 3. And our third step for these is to check those zeros of the first derivative in the second derivative. So we'll take this point, x equals 3. We know it's a turning point, or it's probably a turning point, but we don't really know what type. Well, we can know that from looking at the leading term, but just in terms of our derivative tools here, we don't know, but we can verify that, or we can find out with our second derivative. So second derivative here, if the first derivative is 2x minus 6, second derivative is 2. Just that. So what we know from what we did in class, if our second derivative is positive, that means the function is curving up at that point. Slopes are becoming more and more positive. So if the slopes are becoming positive in this whole interval, but at the same time the slope is flat at a point, that must mean we are at a minimum here. So this point x equals 3 is a minimum. And that's everything for this question. The question is asking us to kind of represent this a little nicely, so we'd have to do some work there. But we do have all the information. So when x equals 3, we have a minimum. And that's it. So this graph function would just look like this, basically. All right. Sorry, I should leave that there. And this is the information I've kind of written out here. So the interval of increase is from x equals 3, this turning point, and beyond to positive infinity. The interval of decrease is everything before that turning point. And we have the minimum when x equals 3. Separately, we can look at our kind of second derivative in those things. We have inflection points. Well, none at all. There's no way to make this equal to 0. So no inflection points. And this function is just concave up the whole time. Never concave down. So from negative infinity to positive infinity, it's just concave up. Okay, that's it for this one. Quite simple. Take a look at our next one here. Oh, yes, so there. All right, this next one where we have x cubed minus 6x squared. Let's just block this one out here. I'm not doing that one. So we're solving this one now. So again, first derivative. Three x squared minus 6. Sorry, not 6x minus 12x. Set this equal to 0. Three x squared minus 12x, and we want to solve for 0 here. We can factor out a 3x, x minus 4 here. Okay, one of these two things must be equal to 0. So we have 3x is equal to 0, and then therefore x is equal to 0, or we have x minus 4 is equal to 0, therefore x is equal to 4. Let's try to draw that x a little better. X is equal to 4. Again, these are the two of our critical points, but we don't know if these are maximums or minimums necessarily. So we use our second derivative, f double prime here. We have 3x squared, so that's 6x minus 12. And we'll check our points with this one. So our second derivative at 0 when x is equal to 0. So 6 times 0 minus 12. So that's negative 12. Okay, so that is negative. And if our second derivative is negative, slopes are decreasing, getting more negative as we go, then that must be a minimum, sorry, other way around. That is a maximum point. And the other one here, when x is equal to 4, so substitute 4 into this, we end up with positive 12. That is greater than 0, and this must be a minimum. Okay. Last part, inflection points. So our second derivative, we want to set this equal to 0, and then therefore 0 is equal to 6x minus 12, and solve that for x. X is equal to 2, right between our maximum and our minimum point. So that is our inflection point. So 0, 2, 4, these are the locations of the critical points. We have a maximum when x is equal to 0. We have a minimum when x is, minimum when x is equal to 4. And then we have an inflection point between the two. So if it's between a maximum and then a minimum, it must be concave down and then concave up, sort of this kind of thing. Okay, so that gives us enough information. Like we can look at the leading term and what we know based on this, but separately, just with our derivative tools, we can also say, okay, so it starts negative infinity, goes up, has a turning point when x is equal to 2, comes down, has an inflection point when x is equal, when x is equal to 0, inflection point when x is equal to 2, minimum when x is equal to 4, and then curves up and goes to positive infinity. Let's redo that inflection point. So about here. That's roughly what the graph of this would look like. We don't know, is it sort of up or down the vertical location, but this is the general pattern that we see. Okay, so from this, we have interval of increase. Sorry, let's label this. So that's 0, that's 2, and that's 4. We have an interval of increase up to 0, and then decreasing down all the way to 4, and then increasing afterward. And minimums are maximum here, minimum here. And just making, okay. Also with our second derivatives here, we have just one inflection point. And we had a minimum points on that. So we can see it's curving down up to that inflection point. And then it is curving up after that inflection point. If there's just one inflection point, then there are just two of these intervals, concave up versus concave down. So concave down, then concave up. So that's the information. But again, if we write that out formally, just use the magic of television here and what I already wrote on the slide, we can see all the information for this particular scenario. All right, that is this one. Next one. Same coefficients, but just the exponents are a little larger. Okay, back. I had to make a brief pause there. Just make sure this audio test. Okay, still good. All right, next one here. So first derivative, 4x cubed minus 18x squared. Set that to 0 for x cubed minus 18, that's 118, 18x squared. Okay, what can we factor out? With the coefficients, we can factor out a 2, and with the x's, we can factor out an x squared. So 2x squared times 2x minus 9, like this here. Okay, so either this is equal to 0 or this is equal to 0. If 2x squared is equal to 0, then x is equal to 0. Or if 2x minus 9 is equal to 0, then x is equal to 4.5. Okay, so two possible turning points. We need to check with our second derivative. Second derivative is 12x squared minus 36x. And we'll substitute in our points here. So second derivative at 0 here, that will just give us 0 and 0. So that whole thing is actually just equal to 0. Okay, so it turns out that x equals 0 is not a turning point. It is an inflection point. Here, an inflection point. F double prime of 4.5. We check our other one. All right, I'm not gonna write out the whole thing and all the substitution. So 4.5 squared times 12 and 36 times, yeah, okay. This would win. The positive term would win here, be a little bit bigger. So the result of this is definitely a positive number. Don't really care what it is. I just need to know it's positive. So in that case, we are dealing with a minimum point here. All right. We are not done finding inflection points though, because we found one of them, but maybe there are more. So we can't guarantee that we found all of them. So we do have a little more work here. So f double prime of x, we set to 0. And if we do that, 0 is equal to 12x squared minus 36x. So we can factor out 12x and we are left with x minus 3. Okay, so x equals 0 is one of the zeros here, and that's, you know, we already found that just kind of by chance with our first derivative. So, okay, good thing that we found that again. It is an inflection point. And our other one, we have another one, which turns out to be x equals 3. So these points here, at 0, we have some kind of inflection point. At 3, we have some kind of inflection point, and at 4.5, we have a minimum. So let's work backward. Minimum is, well, it's a minimum, and this is obviously curving up at a minimum point. If we have an inflection point before that, when x equals 3, when x equals 4.5, we are curving up. So it must mean that at x equals 3, we switch from curving down to curving up. Okay. And then when x equals 0, then while we were curving down, concave down, so it must mean that we went from concave down to concave up. Like this, when x equals 0. Sorry. A few different ways this could go, actually. It could be like this, or it could be like this. Two possibilities. So this is where looking at the leading term is definitely going to help us. We know that both sides are going to positive infinity. So that means that we must have this kind where we're going up. Okay, so putting this together gives us a good sense of what this graph looks like. So it should be, I'll do some blue here. So it's gonna go flat and then inflect and then minimum and then up. So this is when x is equal to 0. We have an inflection point around here where x equals 3. And a minimum where x equals 4.5. Okay, how do I know this one looks like this? That this inflection point is this weird special case where the slope is flat. Well, because this point here, we found the zeros of the first derivative, that means the slope is flat. So the slope is flat and it's an inflection point there. So it's that kind of special case here where x equals 0. then just a regular kind of inflection point where x equals 3 and a minimum. And that's it. That's what the graph would look like. So intervals, when we start, we are decreasing. And then at this point here, we don't increase. It's not a turning point, but we do stop decreasing. So we do very briefly go flat, and then we start decreasing again until the turning point, and then it goes very briefly flat, and then it starts increasing. Okay, so we are decreasing to 0, then decreasing from 0 to 4.5, and then increasing after 4.5. For our second derivative here, we are concave up, sort of curving up, and then we are concave down to 3. Then from 3 afterward, the whole time we are concave up, curving up here. So once again, I have that written out here on the side. So decreasing, increasing, decreasing, minimums, minimum rather, just 1. We have 3 of these intervals for concave up or down. Sorry, I forgot to write in one of the inflection points there. Let's correct that now. X equals 3. Sorry, 1 second, I gotta go help someone. All right, well, I'm back. Zoom. Okay. There we go. We have both of the inflection points at 3 and at 0 for this function here. All right, so one more of these, we'll clear this out, and we'll do, there we go. We'll do the one on the right. So do some quadratic factoring here to solve this one. So we're done with this one. Let's do red. Okay, same process. We're going to do our first derivative. I'm going to change the order. I'll put the largest exponent first. That's usually how we like thinking about this. 3x squared plus 2x plus 1. Set that equal to 0. Negative 3x squared plus 2x plus 1. Okay. Well, factoring a quadratic. This is the thing that we did 2 workshops ago, 2 weeks ago. Lots of ways of doing this. Whatever way you whatever method you like is fine, as long as it's reliable. I definitely like the sum product method. So 2 numbers that adds a positive 2 but multiply to -3. That sounds like +3 and -1. So 3x plus 1 and -x plus 1. Let's just double check here. 3x times 1 and 1 times -x. So that's 3x minus x, that's 2x. Okay. 3x times -x is -3x squared, and 1 times 1 is 1. So, okay, looks like it works. So roots here, f3x plus 1, 3x plus 1 is equal to 0. Then x here must be equal to -1 over 3. Or if -x plus 1 is equal to 0, then x must be equal to 1. All right. So we have 2 points. We need to figure out what types they are, and we'll do that with our second derivative. which is negative 6x plus 2. All right, and we'll substitute in these points. So second derivative at negative 1 over 3. Okay, if we want, however we want to do this, sort of try to just do this in our heads or just substitute it in. So negative 6 here times negative 1 over 3 plus 2. Okay, that's going to be 2 and then also 2. So the whole thing is 4. And that is obviously greater than 0. And our other one here, second derivative at 1 here. So negative 6 times 1 plus 2, the whole thing. Okay, that's negative 4. So that's less than 0. Okay, so these 2 points here. Less than 0, that means we have a minimum, sorry, other way around, it's concave down, so we have a maximum here. And if it's greater than 0, it's concave up, so that means we have a minimum here. Next part, we'll look for inflection points. So we set our second derivative equal to 0. And when it is equal to 0, or when it's 0, so then yes, 0 is equal to negative 6x plus 2, and rearrange and solve here. So x is equal to 1 over 3. 1 second. All right, I have to keep pausing and restarting. Second derivative here, set that equal to 0. So inflection point where x is equal to 1 over 3. So again, this is all the information that we want or that we need to be able to represent this function. So points here, we have negative 1 over 3, positive 1 over 3, and positive 1. Negative 1 over 3 is a minimum point. Positive 1 is a maximum point. And then between the two, we have a single inflection point. So it's from this curving up to curving down like this. Okay, that's enough information for the function. So we know it's going to look like this. Minimum, inflection, and maximum. So similar to the previous, sorry, let's draw that a little larger. Minimum, inflection, maximum. We are decreasing to this minimum points. We are increasing up to this maximum point, and then we are decreasing afterward. And for our second derivative, we are concave up to this inflection point, and then we are concave down afterward. So that is this information, which I misjudged the location of. Let's move that down. Okay. All right, that's everything for this function. So just our kind of regular process here. Find the first derivative. Let's stare into the camera. So you can feel like this is like a live class or something. Find our first derivative, find the zeros of that first derivative, and then check those zeros. So the x values that are the x intercepts, and check those in the second derivative. And that will tell you if they are minimums or maximums or inflection points. Then there might be more inflection points. So we find our second derivative, which we already did in the previous step. And then we find the zeros of that second derivative. It's like really late on a Friday, but there's tons of people coming around to the, don't know what's going on. Find our second derivative, which you've already done, and then find the zeros of that second derivative, and those are the inflection points. So that's it. It's just that process, and we do it a whole bunch of times. Okay, that's enough of these examples. Let's go on to the next section here. This is a quick review, just sort of a visual understanding of what these first and second derivatives look like and where they are, and then we will visual understanding, and then we will look at the actual questions in a moment. So looking at this function here, how many maximums, minimums, and how many inflection points? Hopefully at this point, we can easily recognize that we have a minimum and a maximum. And then in between, we have an inflection point where we change from curving up to curving down, concave up to concave down. Okay, so that gives us 1, 2, 3, 4 different sort of areas on this graph. And the patterns that we'll see in these areas actually are the same, kind of apply to any situation. These are the 4 possibilities. So in each of these cases, we'll say, what is happening with our first derivative? Is it positive or negative? And also what is happening with our second derivative? Is it positive or negative? So in region 1 here, the function is positive the whole time. So f of x is positive, but the first derivative, is it positive or negative? Okay, so the slope is decreasing. For any point in region 1, the slope is decreasing. Decreasing slope. The first derivative is just the slope. So if the slopes are negative, then the first derivative is negative. Second derivative. Here, if we compare, let's do a different color, any 2 points, let's say this point and this point, and we compare the two, the second point has a slightly shallower slope than the first point. The second point is a little more positive. The slope at the second point is a little more positive. It's a bit hard to see there, but we can see, though, looking at the whole thing, that we do have the same kind of curve pattern happening here. It's slightly curving up this whole time. The slopes keep getting a little more positive, a little closer to positive numbers here. Okay, so if it's curving up, remember curving up is just this U pattern like this. So region 1 here is just the first half of that U pattern, but it's still that pattern. So the second derivative is positive. Region 2, function is increasing. Okay, if it's increasing, slopes are positive, then our first derivative is positive. And as we just talked about, if we compare any 2 points and compare the slopes, as we go, the slopes are getting a little more positive. We have the second half of that U shape. That's not curving up a lot, but it is curving up. So second derivative, also positive. All right, hopefully we're noticing the pattern here. Region 3, positive slopes. First derivative, positive. Here, if we compare any 2 points going left to right, as we go, it is getting a little bit less positive, a little more negative. So this is the start of the curving down. Curving down looks like this arch shape. Even if it's just the first half of it, that's still curving down. Or just the second half is still curving down. So here our second derivative is less than 0. And then the last area, hopefully pretty clear by now, decreasing. So our first derivative is less than 0. Second derivative is also less than 0. This is just the rest of that curving down shape. This is that downward arch here. So those are the basic 4 things that can happen. 4 different possible combinations of our first and second derivative being positive or negative. Any function you're looking at, any curve will fall into one of these 4 categories between the kind of turning points and inflection points. So we're just trying to remember these relationships. If our original function is decreasing, then first derivative is less than 0. And if it's increasing, it's greater than 0. Also, if our original function is concave up, that means our second derivative is positive, and concave down means second derivative is negative. Okay, with that reviewed, now we are ready to start the actual questions here. So this is asking us to take some sort of real world scenario with these representations for our variables and say, well, what is f of x doing? What is f prime of x doing? And what is f double prime of x doing here? Okay, population is growing more slowly. All right, well, first f of x, populations, negative populations don't make sense. So population is positive. Second, our first derivative here is growing. Growing means it's getting bigger, it's going up. If a function is going up, sorry, it's not right, positive. Let's write it like this, greater than 0. If the function is going up, then that means the slopes, it has an upward slope. So positive slopes are greater than 0. First derivative is just slopes, so first derivative is greater than 0. Second derivative, it's growing more slowly. So let's say somewhere in the middle, we have this slope. The next point, the next area, is the slope the same? Is it a steeper slope or is it a shallower slope? Okay, so it's growing more slowly. Okay, so there's some change happening. It's not the same. If it did this, then it would be growing more quickly. The rate of growth would be speeding up. So the slope is the rate of growth, and that rate itself would be increasing. But it's growing more slowly. So it's still growing, but the speed at which it is growing is slowing down. So still positive, but not as positive as it was before, not as close to positive infinity. So our second derivative is negative here. And that would give us roughly, let's do this in red. Give us a shape like this. So as we compare, as we move along our slope, our function, the slopes are getting a little bit less positive, a little less steep. So that's this one. Okay. Next one. Actually going to skip the next one for now. We'll come back to it in a moment. So next one here, we have an airplane landing smoothly. So first derivative, so original function, first derivative, second derivative. Airplane lands smoothly, and our f of x is the plane's altitude, so the height of the plane. All right, well, if it's the height of the plane, it can't be under the ground, so original function is greater than 0. First derivative, it's landing, so it's there, and then it's there, and then it's there, and then it's there. Okay, so it's going down. The height is decreasing. So the slope is negative. So first derivative is negative. Then we look at the second derivative. So plane lands smoothly. How does a plane land? So when a plane is coming down to land, it would sort of have a steep, it would come down quickly, but they don't come down really quickly when they're close to the ground because there's a high chance of crashing. So they decrease their rate of descent. They still want to go down, but they want to go down really slowly at the end because if something does go wrong, they don't want to smash into the ground and explode. So like this. Okay. And if we just turn that into a smooth curve, something like this. What does this look like? As we go, the slope was very negative, then slightly less negative, then slightly less negative, and then very close to 0, and then eventually exactly 0. So the rate of decrease here is the rate of decrease in if it's negative, so the change in height is negative, then it's becoming more positive. So it's getting shallower. So that is a positive second derivative. It's the first half of this curving up, concave up interval. Okay. Next one. A stock's price is at its peak. So at its peak, exactly. So stock prices go ... but then it hits some sort of peak here. And we want to know at that peak. Let's redraw that. So at this maximum point here, what's happening? Okay, so first derivative is, original function is positive. Stock prices are always in positive, they're always positive numbers. Our first derivative, positive or negative here? Well, it's at the peak. If we think when we had a maximum point, or also when we had a minimum point, what is the slope at that point? Well, it was exactly 0. That's how we found them. When the slope is 0, what is the first derivative? Well, the first derivative is 0 because the first derivative is the slope. So if something's at the peak, if it's at a maximum point, then the first derivative is 0. Second derivative, maximum points, our second derivative, we are curving down. We have a concave down pattern. That's the only way that we can get a maximum point. So if we have concave down, then that means negative values for the second derivative there. Okay. Note that this question is a little different. The previous questions were sort of what's happening over this period. But here we're sort of talking at like this instantaneous moment. here, just at the very peak, what exactly is happening. All right, next one. The economy is picking up speed. Economy is picking up speed. So this is GDP, gross domestic product. So how much, it's just the sum of all the money made in a country. So that is always going to be positive. Our first derivative, economy is picking up speed. So I guess we sort of have to just understand that this statement always means that it's positive. So the economy is growing. Economies almost always grow. It's quite uncommon for, unless something really terrible is happening, for an economy to actually shrink or contract. So they are, so it's growing. So positive, it's getting bigger. And then also the rate of growth. The rate of growth, it's picking up speed. So it was increasing at one speed yesterday or last year or something. But now it's increasing at an even greater rate. So let's exaggerate that a little bit more. Something like this. Okay, so at this point here, we also say that our second derivative, this is a curving up, concave up interval, second derivative is also greater than 0. All right, that was the last of those ones, but we skipped the one about this one with the bike. So we have a bike and a car and two different sort of acceleration rates and top speeds. So we have a bike that can accelerate more quickly, but has a lower top speed, and a car that accelerates a bit slower, but a higher top speed. Okay, so this is distance. The f of x here, the vertical axis is just distance, it's not speed. So just so we know what this would look like, a constant speed would be this. It's a straight line that's going up. If it's just a straight line that's flat, that means it's not moving because the distance is not increasing. So a straight line that's going up is a constant speed. A straight line that is curving up means it's accelerating. And a, sorry, not straight line, just a concave up line, and concave down means it's decelerating. So negative acceleration. Doesn't mean it's going backward, but it's not accelerating. It's not going faster each time. It's going, the rate of change of speed is negative. So decelerating or negative acceleration. So it doesn't, sorry, that is decelerating. Sorry, let me just think about this one more time. Yep, okay, that's good. All right, so this case is a little more complicated. They want us to compare the bike and the car. It's a little easier to think about the bike first and then the car second, and then finally combine the two of them. So let's do that. Let's color code this properly here. So we're going to do red for the bike, and let's do green for the car, and we can do purple for the bike minus the car. Okay, so the bike is accelerating faster. So this is, again, if it has a constant speed, it looks like this. So the car's final kind of top speed must be steeper than the bike's. But when the bike is starting, its rate of acceleration, so the kind of amount that it curves, like it could be very slightly curved and it could be extremely curved. That's the acceleration rate. So the bike curve should be more curved than the car's curve. It's sort of a steeper rate of increase. So let's see if we can represent that. So it would look like this, I guess. Let's try again. Okay, and then at some point here, it just sort of stops increasing. It hits its top speed. The car, on the other hand, will have a shallower curve, so a more gradual curve. So it will take longer to hit its top speed, but that top speed is higher. So let's say it hits its top speed here. And then eventually it will catch the bike and pass the bike like this. Okay, so these 2 points I've marked are where it would hit its top speed. So what is the resulting function? The red one minus the green one. Okay, well, we have this vertical height. So the height of the purple one will just be this vertical height at each of them. It's 0 at the beginning, and it's going to be 0 right here at this point of intersection. It'll be negative beyond that and positive before that. So it's going to start at 0, and then it will be curving up a bit. 0 and curving. Where do we need to pass? Maximum. Maximum looks like it's about here, I'm going to say. And then we're back at 0 here. All right, so it's going to curve up. And it's going to keep curving up until the bike hits its top speed. And then it starts curving down and hits a maximum point when the car's speed is the same as the bike's speed. Car's speed is the same as the bike's top speed, and then it's still curving down eventually until this point of intersection. And then it's going down like this. Let's do this better. So when the car hits its top speed, then it stops curving and it just sort of goes straight like this. So we have this point, we have this point. All right, it's a little messy, but we have our, so the increase and decrease I think is not super hard to see. We're increasing until this maximum point and then we're decreasing afterward. The second derivative is the more interesting part. So we have our second derivative is positive. We are curving up until the bike hits its top speed. And then we are curving down. So the bike is still ahead, but it's not getting more ahead each time, or the rate at which the rate of change. So the rates at which the gap increases is starting to slow down. So we start curving down here. And we hit this maximum when we're still curving down. Until we hit this point here where the car hits its top speed. And then the second derivative is actually just equal to 0. Excuse me. Second derivative would be equal to 0. And then after that point somewhere, the bike and the car will pass each other. And then the car is further ahead and the car, I don't know, wins the race or whatever is happening here. So that's the pattern. We have second derivative curving up, then curving down, and then going to exactly 0 and staying there when both vehicles are at the top speed. Okay, so a little more complicated. You can kind of see why I left this one for the end. All right, let's go on to the last area. This one, the resulting graph was more or less correct in the workshop. At the ends of the graph, I think I sort of drew it as speed rather than distance. So the ends of the graph were a little bit incorrect in the workshop, but the resulting graph was more or less correct. Okay, let's go to the last part. So just identifying inflection points and the kind of concave up, concave down intervals just from looking at an actual graph. So not making the graph now, we just look at the graph. Okay, well, so this is the more complicated relationship thing that you could be looking at. And these questions, as you'll see, are a little more complicated. So this is definitely the easier thing to learn and try to memorize, but this is the deeper understanding that's worth putting some time into. Okay. So we're going to do these pretty quickly. So let me just kind of jump through them quickly. So 1, 2, 3, 4. Sitting in this chair too long. Need to move around. And 5. Okay, so those are the 5. We will look at these and just quickly identify where the inflection points and concavity intervals are. And then we're going to look at them again and it'll get a little harder. Okay, so I'm just going to kind of go through these pretty quickly and talk about them. If you want to try these on your own, I just showed you all of them briefly, so just kind of jump back and pause on those and try them. All right, inflection points and concavity intervals. So here we have nothing. It's just a straight line. So our second derivative is just 0. There's nothing happening here for us to identify. No curving up or down and no inflection points. Excuse me. Okay, second one, inflection points. Well, we don't see any because we only have one concavity interval. We are just curving up the whole time. We should be writing out the interval notation on the side. I'll just be skipping that for these examples for sake of time. So we're just curving up the whole time. One interval, no inflection points. Next one. Okay, we have curving up here. So concave up here, concave down here. And then we have this inflection point between the two of them. That's it. Here we have curving down, inflection points, curving up. Still just one inflection points and two intervals. And the last one, a little more complicated here. So we are curving down, inflection point here. We curve up. Actually, I need to, it's a little small. I need a more fine writing tool here. So we are curving down. We hit this inflection point and we start curving up briefly, but we have another inflection point and we start curving down again to some inflection point about here. And then we are curving up for the rest of it. So down, then up, then down, then up. 4 of these intervals and 3 inflection points. And we can estimate, it looks like these are happening like -1 and -0.5 and +0.5. Whoa, it's been a long day. Okay. I was going through these pretty quickly because these are actually not what the questions were in the textbook. The textbook is asking this. This is a graph of the first derivative, not the original function, but the first derivative. And we want to figure out what are the inflection points and the concavity intervals for that. So we were looking at original functions and identifying inflection points. Well, let's look at the first derivative. Okay, how can we do that? Well, so what we did, if we remember, when we wanted to find an inflection point, we said, well, if f of x has an inflection point, then our first derivative has a turning point, and our second derivative here is 0. So we found the zeros of the second derivative to identify the location of the inflection points. So we went from the zeros of the second derivative to the original function. But we can also think about the turning points of the first derivative, and those will tell us the inflection points. So here, we have no turning points in this function. It's quite simple. Function does not turn. Our slope is, sorry, not our slope. The slope of the derivative is constant. So there are no turning points here. So we kind of don't have anything in that sense. So we have no inflection points. If we want to know our concavity intervals, where are we concave up, concave down? Well, when f of x is, let's say concave up here, concave up, then our first derivative, what is our first derivative doing? When our original is concave up, our first derivative is increasing. So the slopes are getting steeper and steeper. First derivative is increasing. And our second derivative here is greater than 0. It's some positive number. So this is what we did again to find these concavity intervals. So when we did our turning point tests here, we used the second derivative, and then we said, okay, based on that, the original function is concave up, and based on that, our turning point must be a minimum. But we can also just say, well, from the first derivative, if the first derivative is increasing, then we must also have a concave up pattern there. So here we have first derivative increasing, first derivative increasing for the whole thing. So that means for the whole function, we are concave up. So from negative infinity to positive infinity, the whole time the function is curving up. Basically, we have some sort of quadratic like this. We don't need to draw that. That's a very good application. I would recommend that you try that, but that's not critical here. All we need to be able to recognize is that it's concave up because the first derivative is increasing. Okay, so let's do that. Let's take this kind of logic and thinking here and look at some harder ones. So we're looking for turning points in our first derivative. If we have a turning point in the derivative, we have an inflection point. If we have an increase in our derivative, we have concave up. And then also decrease in our derivative is concave down. So the thing on the right is the opposite for concave down. First derivative is decreasing. Second derivative is negative, less than 0. All right, let's try. So this one, first inflection points. Do we have any? Well, again, this is the first derivative we're looking at. So we're looking for turning points. Do we see a turning point in our first derivative graph? Yes, we do, right here. So x equals 0 is an inflection point, again, inflection point of the original function. So this graph of the derivative lets us know this information about our original function. Okay. Then what else do we have? So if our first derivative, we said if it's increasing, then we have a concave up pattern. If our first derivative is increasing, then the original function is concave up. So we must be concave up from x equals 0 to positive infinity, and concave down from x equals negative infinity to 0 on the other side. Because our first derivative is negative. And the first derivative is negative, that means we are concave down. Okay, so I know you might be looking at this and saying, well, no, it's concave up the whole time. This isn't the original function. This is the first derivative. Good application again of this would be to take this first derivative, try to work backward and say what the original function would look like. What does the original function look like here? This one is not so bad. So slopes are big positive numbers. Less positive, slopes go 0, and then the slopes go positive, positive, positive again. So it's basically an x cubed function like this. That's what the original function would look like. Okay, so we had one inflection point and 2 of these intervals, concave up and down. Next one here. Okay, turning points. Do we have turning points? Well, no, we don't. We have this point where the slope is flat, but that's not a turning point. We've talked about this a few times. Does not qualify as a turning point because this function doesn't turn. It doesn't start going in the other direction. So no inflection points here. Okay, then concavity intervals. So we have an increasing slope and we have an increasing slope here. So at the very least, we are concave up. Let's do this. We are concave up after 0 here, and we are concave up before 0 here. But right at the spots, technically we are not concave up. So concave up and then flat and then concave up again. This is a graph of, I know I said that this would be a good application, but yeah, I'll just sort of show you here. This would be a function of x to the exponent 4. f of x equals x to the exponent 4. So it has a turning point, but then also the second derivative goes flat briefly. So that's like a third derivative test. We didn't get into that in class, so you don't need to worry about that so much. But at least we can see we have these two intervals of concave up on the outsides here and no inflection point because we have no turning point. All right, two more of these. This one is not so bad. So here, inflection points, we are just looking for turning points. So turning points and turning points, these must be inflection points of our original function. So at 0 and 1, we have inflection points. And then we are so if our first derivative is increasing over here on the right, then we must be concave up there. And if our first derivative is increasing on the far left, we must be concave up there. And if our first derivative is decreasing in this middle part, we must be concave down here. Okay. So this would turn into a concave up, a concave down, and a concave up, and be this sort of function. Roughly. I'm not being very careful with like the relative heights here, but it is this sort of x to the exponent 4 that goes down, up, like this. 3 of these concavity intervals, and with 2 inflection points like this. Okay, last one. Definitely a little more complicated. All right, so what's happening here? Same process, it's pretty straightforward. We're just saying we have a turning point here and we have a turning point here. Let's just do that. Turning points, turning point. So those are the 2 inflection points at 0 and 1. Okay, so on these other ones, we have first derivative increasing. So this must be concave up from 1 to positive infinity. We are decreasing here from 0 to 1. So this must be concave down. Okay, we have another point here where the slope goes flat. It's not a turning point, so it is not an inflection point. But the second derivative does go to 0 here. So the concave up, concave down pattern does stop for a moment. So we are increasing here over this interval from -1 to 0. So we are concave up that whole time. And then before -1, function is positive. The first derivative slopes are positive here. It's increasing. So that means we are concave up. So this function is slopes are very negative. And then slope hits 0. And slopes go positive, and inflection points. Slopes are still positive. And they go flat. Okay. I did not work this out on my own. I'm trying to just puzzle this out for myself quickly here. Yeah, I'm not 100% confident that that's correct. I would have to spend a little more time thinking about this, but I'll leave that as an exercise for you. What would the original function of this look like? So that's definitely a harder thing. But again, turning points and just, is it increasing or decreasing? That's all we need to be able to identify these inflection points from the first derivative. So it's the exact same just visual identification we did of finding the turning points and increasing, decreasing intervals from the original function. We're just looking for the same kinds of things. Just by chance, we are looking at the first derivative and then using one logical kind of extra step there to figure out what's happening with the original function. So some good application here. If you didn't fully understand those, then okay, answers are gone. Go back and look at them again, try them on your own and see if you can understand what's going on here. These questions here are not really like a common thing you have to do. It's, can you do it in reverse? If you understand it well, you can do the same process. You can work this in reverse and see what's happening. Okay. All right. That was a while, but we finished these questions here. The first parts that we did, just finding the critical points, the turning points and the inflection points using the derivatives. That's by far the most important points. The other parts here are just some kind of more complicated, deeper understanding examples. So if that stuff was a bit hard for you, don't worry about it so much, but definitely those first 4 questions, you need to be able to do that stuff and those processes. All right, that's it. I don't need this question slide here. So that was workshop 12, a little better, a little more thoroughly explained, which took quite a bit of time. And this is why we did not have time to do this in the actual workshop. But here we go. It's a nice video that will live on forever. And I will go home and finally get some rest. I hope this is useful for you. See you in class.